8.1, the law of sines, continued. In our previous video, we talked about the law of sines being used to solve case 1, where we had two angles and a side of a triangle. And with that, we were able to use those two angles to find the third angle. We were able to use the law of sines to find the two missing sides. The case we're going to deal with now is case 2, which is where we have side angle. We have two sides, and we have the angle opposite one of those sides, but not the angle in between them. Now, that doesn't seem too bad. If we have two sides and an angle, then we can obviously find the other angle. And then once we've got two of the angles, we can find the third angle. And then if we've got that third angle and we've got two of the sides, we can find the third side. So using the law of sines. Not too bad. The problem is, case 2 is also known as the ambiguous case. And you may ask, why is it known as the ambiguous case? And that's because case 2 runs into some issues. Because we have two sides and an angle opposite one of those sides, we don't have the angle in between, three different things can occur. One, we could have a side, an angle, and if you look at this drawing here, this is just done really small to indicate we have the angle, so we know where that's going, but we don't know the length of it. So you could say that's going to go on who knows how long. Since we don't have the angle in between these two sides, we don't know where that goes, but I see a problem here already. If you look at the length of this side, it's that long, and I draw it here, it does not make it to this side here. So given the length of this side, the length of that side, and this angle, we find out that this side is too short, and therefore we have no triangles that we can create using that information. So generally, this is an oops setup. We're given two sides and an angle that's opposite one of those sides, and it's impossible. There is no triangle that will fit that criteria. And we have to be able to recognize that. Well, what can we do to recognize it? Well, first of all, we can realize that this side is shorter than this side. So if I call this side A and this side B, let me make that A a little bit bigger for you. A and side B, our first indication that we may have a problem is that B is smaller than A. That by itself doesn't guarantee that we're going to have no triangles. But it's an indication that we may run into that situation. What's going to be our dead giveaway as we do this is, since we have two sides and an angle, we're going to have to use law of sines to calculate one of the other angles before we can do the supplementary angles to get the third angle. And when we do that, we're going to run into an error, because to find that missing angle, we're going to have to take the inverse sine or arc sine of some value. And if we find out that that value is too big, because remember, sine goes from -1 to +1. So if we find that that value is outside of that range, or I should say that domain, then, actually the range was correct, outside that range, then we are going to find out that we cannot make a triangle. So what's going to happen is, if this is the case, when you start to do law of sines, you're going to go to find their second angle, and your calculator is going to give you an error because it's impossible to have those sides associated with an angle. So that's our first possibility. We have no triangles. Our second possibility, and what I would consider the optimal thing to have happen, is we're given a side, we have the angle, so we have this side, we have that side, we have this angle. We're going to call this A and this B, just for comparison's sake. We know that this is going to continue on, but we don't know how far. This is optimal because if B is greater than A, if B is longer than A, then we know we're not going to run into the problem of it being too short. So it is going to form a triangle, and if this is the case, it will always form exactly one triangle. There will be one triangle that will be able to be solved for with these two side lengths and that angle. Now please let me remind you that do not get set on B less than A, B greater than A. Because depending on which angles or sides you are given, those may not be the letters involved. Just remember, we're looking at the side opposite the angle given and the side adjacent to the angle given. So if the side opposite the angle given is smaller than the side adjacent to that angle, then we're at risk of no triangles. If the side opposite is longer than side adjacent, then we're in this case where we're guaranteed to have exactly one triangle. The third possibility, let me make this just a little bit bigger here, is that second side so we have the side, we have the angle opposite one of them. It's that this second side is smaller than that first side, so we call this A and that's B. So B is less than A. So if B is less than A, again, that's where we ran into here, but this time B is long enough that it does cross that other line. But what this has is, since B is shorter than A, there is also the possibility that it goes the other direction to create an obtuse angle here instead of the acute angle here, because nothing tells us how long this bottom line is. We just know the length is, and if you think of it as a pendulum, right, it can swing back and forth, and if it's shorter than A, it can cross this line of who knows what length in two different spots. Therefore, we can have two triangles. And thus we see why case 2 is called the ambiguous case, because we could either end up with no triangles, one triangle, or two triangles. And if we end up with two triangles, then we need to find both of those triangles. Again, don't focus on the A and B, focus on opposite versus adjacent. If the side opposite your angle is shorter than the side adjacent to your angle, then that puts you either into no triangles or two triangles. If it's longer than the side adjacent, then you have exactly one triangle. So you're basically looking for these things. If the side opposite's longer, good, you've got one triangle, just solve it. If the side opposite is shorter, you're either going to have no triangles or two triangles. How do you tell if you have no triangles versus two triangles? If you go to solve it and you run into an error because you're trying to find the inverse sign of something greater than 1, then you have no triangles. If you don't run into the error, then you've got to watch out and make sure that you account for both of these angles and you come up with 2 separate triangles that could satisfy this. So that's fun. So let's put this to work. I'm going to try to erase this such that I don't get blue smearing everywhere. I apologize for that. That showed up really bad on the screen. I have a blue marker that is determined to just smear all over the place, so I need to clean off the eraser. Okay, so I'm going to get rid of this ambiguous case thing. We don't need that. And I'm going to get rid of the case 2. We don't need that. But I'm going to leave our law of signs up here. So let's look at one. So I'm going to pull an example that I already have, where we are given the triangle as follows. Side A is equal to 17.9 centimeters. Side C is equal to 13.2 centimeters. And angle C is 75.5 degrees. So we've got 2 sides and an angle. The angle is opposite one of the sides, so let's just draw that. Now I'm going to draw it again as just a basic triangle and not really pay attention to whether this actually fits the measurements or not. We'll look into that a little bit later. So we have C, A, and B. Side A is 17.9 centimeters. Side C is 13.2 centimeters. And angle C is 75.5 degrees. Okay, so we have side-side angle. Now notice this is opposite what I drew when I was doing my examples of no triangles, 1 triangle, 2 angles. Doesn't matter. Your angle could be any of these 3. Your sides could be any 2 of those that are not surrounding that angle. So I look at this and I compare the side opposite to the side adjacent, and I see that 13.2 centimeters is smaller than 17.9, so I'm just going to point that out. 13.2 centimeters is less than 17.9 centimeters, which means we're going to have either 0 triangles or 2 triangles. Just cheating using a triangle, or to say triangles. Because the side opposite is shorter than the side adjacent. So either it's going to dangle there and never touch side B, or it's going to touch side B in 2 possible locations. The only way to determine that, really, is just to go forth and start doing our calculations and see what happens. So we have side A, side C, and angle C. So we're going to take A over sine A is equal to C over sine C. So let's plug them in. So we have 17.9 over the sine of A is equal to 13.2 over the sine of C. I'm sorry, C is 75.5. Okay, again, we're trying to get to this, we're trying to get to A. We have a proportion, so I can say sine A is equal to the product of the diagonal divided by what's opposite. And I'm going to write this out here. So sine A is equal to 17.9 times the sine of 75.5 degrees over 13.2. So let's grab our calculator and see what happens with that. So 17.9, sine of 75.5, oops, not 57, 75.5, yeah, 5, sine gives me 0.9618, sorry, 0.968147, etc., etc. Multiply that by 17 and we get approximately 17.3298. Divide that by 13.2. Let's try that again. I hit the wrong button, sorry. 17.9, 75.5, the sine of that. And then divide, I accidentally hit multiply, so it came out very interesting. So sorry, I'm going to multiply that. That's good. But then when I did the 13.2, I accidentally hit multiply instead of divide. I divide and I get that the sine of A is equal to 1.313 approximately. Now I can plug this into the calculator to find A. I can say A is equal to the inverse sine of 1.313. And what's going to happen? I'm going to get an error because the sine of A cannot be 1.313. Because the sine of A must be between -1 and +1. In fact, we're dealing with a triangle, which means that the angles must be less than 180 degrees, each angle. Therefore, we've got to be in the first two quadrants, so the sine of A has to be between 0 and 1. But if you just go sine in general, you cannot have the sine of an angle equal to 1.313 unless you have a multiplier in the front, and we don't. So we get an error, which tells us there are no triangles that fit this information. Basically, 13.2 is dangling there and never touches side B. So no triangles. So that's one thing that can happen to us. And notice when we start working our way through, when we try to find that angle, we get an error. And if you plug that into your calculator, see that that's exactly what happens. So therefore, no triangles. So there's one possibility. Let's try another example, and again, I'll pull this from my ones that I've already put together, just to make our life a little easier. Just trying to find the other example I'm looking for, okay? So here we go. So angle A is equal to 61.4 degrees. Side A is 35.5 centimeters. Side B is 39.2 centimeters. Draw a triangle so that we can put this together. So we have A, B, C, A, B, C. Angle A is 61.4 degrees. Side A is 35.5 centimeters. Side B is 39.2 centimeters. Okay, so there's our start. So we start there. Let's look and see. Compare the side opposite to the side adjacent. And again, we see that 35.5 is less than 39.2. So the side opposite is shorter than the side adjacent to it. Therefore, we're going to have either 0 or 2 triangles. If this side was greater, then we know we'd have one triangle, we just go through the work and get it done. But now that we have that, we have to determine, is it no triangles, or do we have 2 triangles? If we have 2 triangles, we've got to find both of them. So let's work through this. I'm going to switch to red just because I want to show the work that we're doing versus what was given. So our first step, since we have side A and angle A, and side B, we're going to use law of sines to find angle B. And I'm not going to write out the law of sines this time, I'm just going to put it together. So side A is 35.5 over the sine of A, which is 61.4 degrees, is equal to side B, 39.2 over the sine of B. So if this isn't going to work, we should run into a problem right away with finding B. So let's see. So sine of B is equal to, multiply the diagonal, 39.2 times the sine of 61.4 degrees over, divide by what's opposite, 35.5. So sine of B is equal to what? So we got 39.2. The sine of 61.4 is approximately 0.87798. So we're going to multiply those together, give us approximately 34.417, and then divide by 35.5, which is good. This came out to be 34.417 approximately. This is 35.5. That's larger than it, so we're going to get a number less than 1. 35.5 divide, and we get the sine of B is approximately equal to 0.9694910609192. Now, I would suggest keeping as many digits as possible. Optimally, once you've got that value, tell your calculator to take the sine of it directly. Many calculators have an answer key, meaning there's a button on it that actually says ANS, or a shift function on a button that says ANS, so it can actually take the answer. So you take the sine of answer, and you can use as many digits as your calculator will allow. Otherwise, use as much as you can here so you can get the angle as close as possible. So if I take the inverse sine of this, I get B is equal to 75.81068 ... Since our angles are to the nearest tenth, I'm going to say that's approximately equal to 75.8 degrees. So that is this angle here. Now the thing that we have to note is this is less than 90 degrees. Since this is shorter, it could swing wide or it could swing narrower. So this is a reference angle. I'm going to call this B1. There's also the possibility that this could be an obtuse angle. So 90 plus this. Actually, I shouldn't say 90 plus this, right? So this could be an obtuse angle. So here we've got it as 75.81086, 100868, etc. So 75.8. We should subtract that from 90. So 90 minus 75.8 degrees gives us 14.2 degrees. So we're on one side of 90, or we can be on the other side of 90. So that would give us 90 plus 14.2. So B2 is equal to 104.2 degrees. So it's either 14.2 degrees less than 90, or it's 14.2 degrees greater than 90. So those are our two possibilities for B. We are now going to solve angle C and side C for both of those possibilities. Notice that I called the first one B sub 1 and the second one B sub 2. So I've got these two possible triangles. They're both going to have A equal to 61.4 degrees and sides A and B equal to 35.5 centimeters and 39.2 centimeters. Those are going to stay the same, but they're going to have different angles, and that other side is going to be different. So we have B1 and B2, which means I can now find C1, which can be done simply by taking A and B1 and adding them together and subtracting from 180. So I've got 61.4 plus 75.8, which gives us 137.2. If I subtract that from 180, I get 42.8 degrees. So using B1, that's C1. If I use B2, I can get C2. So I take angle A, 61.4 degrees, and I add 104.2, which gives me 165.6. I subtract that from 180, and I get 14.4 degrees. So I've got one triangle with angles 61.4, 75.8, and 42.8. I've got the other triangle with angles 61.4, 104.2, and 14.4. Now the only thing left is to find side C. So I can do that using this angle, and I don't even need to use this angle. I could, but remember, we like to use as many of the original angles as possible. So I have angle A and side A, so let's use that and this angle to find side C, and then we'll do the same thing here. We use angle A and side A to find, and this angle to find side C. So I've got A over sine of A, so I'm going to go 35.5 over the sine of 61.4 degrees is equal to lowercase c1 over the sine of 42.8 degrees. We want to find lowercase c1. We multiply the diagonal, 35.5 times the sine of 42.8 divided by what's opposite, the sine of 61.4. So we have 35.5. The sine of 42.8 is approximately 0.679. I'm going to use as many decimal places as I can. So when I multiply those two numbers together, I get 24.12 approximately. And then I take the sine of 61.4, which is about 0.87798. And I'm going to divide my 24.12-ish by approximately 0.87798. And I get 27.472248 ... But our sides are only to the nearest tenth of a centimeter, so C1 is equal to 27.5 centimeters. So my first triangle has angles 61.4 degrees, 75.8 degrees, and 42.8 degrees, and sides 35.5 centimeters, 39.2 centimeters, and 27.5 centimeters. That's my first triangle. Due to lack of space, well, I was going to say due to lack of space here, I'm not going to combine them, but I really want you to combine these things. So I'm going to take the moment and come over here, and I'm going to put the first solved triangle together. I've already got this A, and B, so I'm going to add in B1 is equal to 75.8 degrees. C1 is equal to 42.8 degrees. And lowercase c1 is equal to 27.5 degrees. You should always put the answer together in some way rather than making someone search through all your work to find all the values. So there we go. So that's triangle 1. I'm going to put triangle 2 right below it. So if we're doing that, now we've got our second C angle, C sub 2. We're going to do the same thing. 35.5 divided by the sine of 61.4 degrees is equal to lowercase c2 over the sine of 14.4 degrees. So c2 is equal to multiply the diagonal, divide by its opposite, so 35.5 times the sine of 14.4, which is approximately 0.2487. Multiplying together, we get 8.83 approximately. Divide by the sine of 61.4, so 61.4, the sine of that is approximately 0.878. So when we divide by that, we get 10.055, etc. So 10.0554, ... Again, our original measurements were to the nearest tenth. So I'm going to round this to the nearest tenth. C sub 2 is equal to 10.1 centimeters. So now I have those. So I'm going to put this here. So B2 is equal to 104.2 degrees. C2 is equal to 14.4 degrees. And C2, the side, is equal to 10.1 centimeters. So we have our first triangle and we have our second triangle solved. And of course, angle A, side A, and side B are the same for all of those for both of those because that's what we were given. So that's what happens if we end up with two triangles. Notice that we didn't run into any errors during our calculations. We just had to recognize the possibility of two triangles because the side opposite was shorter than the side adjacent. And when we did that, we then took the angle that we found its complement, and used that to find the other possible angle. The other way that you can do that, we found the complement and said, okay, if we subtract it from 90 degrees, then we get 14.2, and then we added that to 90 degrees to get this. The other possibility is you take the supplement. So we had 75.8. If we subtract that from 180, 180 minus 75.8 gives us 104.2 degrees. So to get your second angle, either use the supplement, find its supplement, or find its complement and add that to 90 to get it. Either way, whichever one you prefer, makes no difference as long as you do it right. So there we go. So that's the ambiguous case with two triangles. I'm not going to do an example of one triangle because we did more work to find this than we do to one triangle. If we come out with one triangle, the side opposite is longer than the side adjacent, which means you just go through this work once and you don't have to find a second triangle. So it's actually less work than what we've done. So that's finding case 2, the ambiguous case, either no triangles, one triangle, or two triangles.